All right, I think we're live. So, hello people, and welcome back to the Latin American webinars on physics. This is Joel Jones again from the PUCP in Peru. Our webinar today is given by Arsenii Titov, who is a postdoc at the University of Pisa in Italy. This is webinar 170, and Arsenii will tell us about a recent work of his and his collaborators involving solutions to the strong CP problem using modular invariants. Before we begin, let me tell you a bit about him. So after completing his PhD at Pisa in Trieste, Arsenii moved to Durham, UK as an early-stage researcher within the LUCIVS program. This was then followed by postdocs at Padova and Valencia before moving to Pisa. Okay, now, as usual, let me remind viewers that you can ask questions and make comments via the YouTube live chat system, and this will be passed on to Arsenii at the end of the webinar. So, okay, feel free to begin with the talk.
Yes, first of all, thank you very much for the invitation and for the opportunity to present my recent work. So let me share it now. Okay. So do you see my screen well?
Perfect.
Okay, perfect. So then I will start. So thanks again. And today I'm going to talk to you about solving the strong CP problem without axions. So this is the proposal which comes originally from the work with Ferruccio Ferruglio from Padova and Alessandro Strumia from Pisa. And also our recent work, also in collaboration with Matteo Paricciato, who is a PhD student at Roma Tre University. And so I'm going to discuss a bit what we proposed in these works. So first, here the outline of my talk. I will start with recalling the strong CP problem and very briefly summarizing the existing solutions. And then I will dedicate some time to describing the most general conditions for solving the strong CP problem by spontaneous CP violation. So I will present you with a certain QFT realization based on certain flavor symmetries, either U1 or modular invariant. So I will dedicate some time also to introducing this interesting symmetry. And finally, we'll present with concrete models based on this modular invariance. So let's start. So what's the strong CP problem? The strong CP problem goes as follows. So the QCD Lagrangian written here, principle has two parameters or two terms which can violate CP. So first is a Quark mass matrix, which can have complex phases, which violate CP. And the second is the, let's say, this GG dual operator, so a topological operator, which is a total derivative, but has some physical effects at non-perturbative level. And actually, the physical CP violation parameter is given by the combination, so I will denote it by theta bar, which is given by the sum of this bare theta QCD term and the phase of the determinant of the Quark mass matrix. And in particular, this theta bar parameter contributes to neutron electric dipole moment. So here is the estimate how it contributes. And the point is that experiments set very strong limit on this quantity, on this neutron EDM, of order of 10 to the minus 26 E per centimeter, which translates to a bound on this theta bar parameter of order of 10 to the minus 10. So the question arises why this parameter is so small, and once naively we expect it to be of order 1. But this is only one part of the problem. Another part of the problem that we know that actually in weak interactions CP is violated by the complex phase in the Kabibo-Kobayashi-Mascava quark mixing matrix, and indeed this phase is of order 1. So there are, of course, several solutions have been proposed to this problem, and the most probably famous one or known one is the axiom. So here is the idea is to promote this theta parameter to a dynamical scalar field, the axion, which couples in the low energy EFT to this GG dual term. Then QCD generates a potential for this scalar field such that the minimum of this potential is at zero. So somehow theta relaxes dynamically to zero, which washes out CP violation in QCD. So this solution relies on an assumption that there exists a new global U1 symmetry, U1 PCA queen, which is spontaneously broken, but in addition also anomalous under QCD. So this implies that actually axion is a pseudo Nambu-Goldstone boson. So it's a very light scalar field. So this solution got lots of attention because it provides a clear experimental target, so a new light scalar particle. However, till now, the experiments, there are many searching for the axion, they did not find it. And also there is some theoretical problem associated to this solution known as a quality problem. Basically, very briefly, in quantum gravity is believed to break all global symmetries. And actually here, a higher dimensional operators, which will go as the powers of Fa, the scale of PCA queen symmetry breaking, to the Planck mass, they would contribute, would give corrections to theta bar. And since theta bar is very much constrained, these corrections should be extremely small. And actually, this was sometimes referred to that in concrete models, this U1 PCA queen should be an accidental symmetry of a good quality. Okay, so however, so in the absence of the axion, it's also worth investigating alternative proposals, and another big class of solutions relies on the assumption that either parity or combined CP symmetry, so charge parity, is a good symmetry of the UV theory. So then if we look at this GG dual operator, it is P odd but C even, implying that it is also CP odd. So then if we assume that P or CP is a good symmetry of the UV, then this term should be absent. So then the challenge is to break P and CP spontaneously such that this theta bar remains zero while delta CKM of order 1 gets generated. And note that actually in the SM both P and CP are broken explicitly, and this calls through BSM extensions. So first extension, very briefly, is based on assuming that parity is a good symmetry in the UV, and actually this proposal came soon after the axiom was proposed. However, so since parity is badly broken in the standard model, the extension should be rather large. Usually the extension relies either on a new extended gauge group, we can think about left-right symmetry, or some extension with mirror worlds and mirror fermions. So let me give you some concrete example from this paper by Babu and Mohapatra. So they assume left-right symmetry with two Higgs doublets, so one charged under SU2 left, another under SU2 right, and then also so quarks, now left-handed and right-handed, both of them they are doublets of the respective SU2, and in addition there are some heavy vector-like singlet quarks. So then the full mass matrix for the colored fermions has this form. So here 0 by gauge symmetry, and then, okay, so here we have Yukawa times the wave of the left Higgs, Yukawa times the wave of the right Higgs, and this is the vector-like mass term. So then the determinant of this mass matrix is real if these waves are real, and indeed in this model they can be made real by independent gauge rotations. So this leads to argdet 0 at 3 level. So good, but requires rather a lot of new stuff. Second proposal is based on assuming that CP is a good symmetry of the UV. In the standard model, actually CP is broken only by the Yukawa couplings, Yukawa interactions. So perhaps here the extension should not be so drastic. The idea goes as follows. So one promotes Yukawa to dynamical variables, which usually depend on other fields, and then one needs to break CP spontaneously. So here the typical examples, the models proposed by N. Nelson and Barr 40 years ago. So what did they propose? They proposed to introduce new vector-like quarks and a set of scalars Z with CP violation waves. And now the mass matrix of colored fermions has this form. So in this light block, we have a breaking. So this fills the breaking of electroweak symmetry. So here we have 0. In principle, would be good to impose this 0 by a symmetry, but till now it's just an ansatz. And in the mixing between heavy and light quark, we have this Z wave, which basically breaks CP. And this is a vector-like mass term. So since CP is a good symmetry, all the couplings in this mass matrix are real. So the only source CP violation, these waves of Z, and the determinant is real and can be made positive. So then the light effective quark mass matrix depends on these waves of Z, which produces a non-zero delta CKM. So good, but again, actually some additional matter, these vector-like quarks are needed. Also, there is usually some tuning between the scale of this wave and, let's say, Planck scale, and also loop corrections are usually dangerous, but can be maybe tamed a bit with supersymmetry. So now let's go to our proposal. So first I consider very toy model with only 2 generations of quarks and try to identify the generic conditions which solve a strong CP problem by spontaneous CP violation. So assume that quark mass matrix, let's say MD, has this form. So each element is proportional to some power of this scalar Z. And the constants Dij are real because I impose CP invariance. Now, the full quark mass matrix, which is given by the direct sum of MD and MU, has this determinant. This times similar from the up sector. So what do I want? I want that this determinant is a positive constant which does not depend on Z, no? Which introduces, let's say, the CP violation parameter. So then I look at this determinant and conclude that if K11 plus K22 equals K12 plus K21, then the dependence on Z factorizes, and actually I have something like real constant times Z in a certain power, which is given by the sum of over, down, and up quarks. So now, if this power is 0, then indeed I achieve what I want. I achieve that that of MQ is that independent real constant. Okay, so there is an interesting class of solutions to these equations, and it is given by this formula here, that basically the degree of each element in the Yukawa coupling is given by the sum of the charges of right-handed, left-handed, and Higgses. Left-handed quarks and the Higgses. So actually these charges, they are defined up to some additive constants. Okay, it's not so important at this point. And indeed, as I will try to show, they can be interpreted as charges in models with U1 flavor symmetry, or later we will see also as modular weights in models with modular flavor symmetry. So let me give you a simple example. Assume I have some U1 flavor symmetry. So now I say that my matter fields, quarks and Higgses, they transform like this. And the scalars, they transform like this. So here is this plus just my convention. So I will use plus sign for the scalars and minus sign for the fermions. So the typical Yukawa entry has this form. And then, indeed, in order to balance the charges of these matter fields, this power of the scalar field should be as I wrote here. So now then the total power is 0 if this sum over the generations, right-handed and left-handed quarks, and the Higgses is also 0. So let me give a bit more words about this toy model. So assume now I assign some positive charges to the first generation right-handed quarks and negative charges to the second generation right-handed quarks and the opposite for left-handed quarks. Then I end up with this simple mass matrices for down and up sector. So all these D11, U11, etc., they are real constants. And here I have a positive power of z. Here I have a negative power of z. So in particular, in the limit, when z goes to 0, these elements to 1, they become singular. So what does that mean? Actually, if I view this model as some effective field theory, then it means that actually my EFT breaks down. Because in the full theory, I have some massive states which I try to integrate out, but they accidentally become massless. So if I want to avoid this situation, this breakdown of EFT, I should impose that this singular element would be singular elements be 0. So if then they are 0, I have this very simple form of Quark mass matrices, basically 0 here, imposed by my requirement, then real constants on the diagonal, and some positive power of z here in this anti-diagonal. Okay, so but we know that actually with 2 generation of quarks, it's impossible to have physical CP violations, so we need to go to 3 quark generations. But even in this case, having only one complex scalar z is not enough, because one can show that actually all the phases can be rotated away. So what we need at least 2 complex scalars, Z1 and Z2, with a relative phase between the waves to produce physical delta CKM phase. So let me give you again some examples. So I assume one singly charged scalar and one doubly charged scalar, and assign charges -1, 0, 1 to 3 quark generations. So then again, assuming no singularities happen, I have this texture. So upper triangular block is 0, then real coefficients along the anti-diagonal, and the complexity sits in this block here. So crucially, as I said, the phases of this double charged scalar and singly charged scalar should not be aligned. So if they are not aligned, I can have so real determinant of this matrix and non-trivial delta CKM. So then one sits and writes the generic conditions under these assumptions to solve, let's say, to solve this problem. First requirement that the Yukawas, they actually should be polynomials in these z variables. We can think about them as scalars. And the powers here, exponents, should be greater than 0 in order not to have singularity. Then the second condition that the Yukawas, these polynomials, should be weighted homogeneous polynomials of certain degree, meaning that they scale like this. So if this is true, that's also the determinant of the Yukawa matrix will be a weighted homogeneous polynomial with the total degree given by the sum of this case here. Finally, in order to have the determinant of the full quark mass matrix being constant, we need to ask for its 0 degree. So basically this sum du plus dd should be 0. And then, okay, so here is concrete example, assuming that each element in the Yukawa matrices has this power given by the sum of right-handed, left-handed quarks and the Higgses. We can see that indeed these powers du and dd have this form, and then the total degree is just given by this sum over the generations plus Higgses. So under the assumption that there are no other heavy quarks, only standard model quarks, and so these conditions can be realized, and there are only 3 independent patterns of Quark-Yukawa matrices up to, let's say, permutation of columns and rows. So the first pattern is somehow not interesting because it has real Yukawas, no complexity. The second pattern, characterized by, let's say, 5 real constants, 2 zero elements, and 2 elements which have complexity. And the final pattern, which I already demonstrated you at some examples, is of this form. So some triangular block is 0, then real constants on the diagonal, and complexity sits here. So there are not so many possibilities. Now let's see if we can realize these patterns in concrete QFT. So I said that I assume that Yukawas depend only on Z and not on complex conjugate variable Z bar. So this somehow calls for supersymmetry, because we know that in supersymmetry, in particular superpotential, which parameterizes Yukawa interactions, is a holomorphic function of superfields. So here you can see the most general n equals 1 global supersymmetry action. So it's characterized by 3 functions: the Keller potential, which contains kinetic terms and gauge interactions, and the superpotential is holomorphic function of fields which parameterizes the Yukawa interactions, and F is gauge kinetic function, which contains the gauge coupling and bare theta QCD. So in what follows, so I split the fields in M and Z. Z, they are these, let's say, scalar fields. We will think about them as dimensionless gauge invariant chiral superfields, spurions, and M are matter fields, basically the quarks, leptons, and the Higgses. So now I want, on top of a requirement of supersymmetry, also ask for invariance under the following, let's say, flavour-like transformation. So each matter field transforms with some charge or some power minus k, and the scalars, these z operators, they transform with a positive power. Now, in principle, there are many possibilities, because these transformations can be either global or local. So if they're local, they form a gauge group, and this gauge group gamma can be either continuous or discrete. Furthermore, this gamma can be either linearly or non-linearly realized. So in what follows, I will discuss these different situations. But first, just looking at the superpotential. So now you see that Yukawas, they are functions of these fields Z, and just knowing how the matter fields transform and how Z transform, we conclude that indeed Yukawas should be weighted homogeneous polynomials of this degree given by the sum of the charges. Okay, so now let's go first to linearly realized gamma. So if the symmetry is linearly realized, it means that the transformation depends only on the group elements. And these scalars, that they're elementary scalars. So here we have the transformation for matter fields and for these Z fields. And then the invariance of the Keller potential under this transformation implies basically that vector supermultiplet, which sits here, also have certain transformation properties. At the same time, if symmetry is not linearly realized, this means that there appears a new player in the game, a new field which I will call tau. And now both the transformations and also these scalars depend in turn on tau. So the scalars in particular become composite objects. And why it calls non-linearly? Because tau itself undergoes a non-linear transformation under this group gamma. So now for M and Z, the story repeats itself, but with the difference that both lambda and z now also depend on tau. And the Keller potential on top of this contribution for matter fields also involve a contribution which depends purely on this new tau field. So in what follows, I will try to exemplify this generic discussion, but before this, let me go back to linearly realized and simple U1 symmetry. So then this lambda is just a phase rotation. So then the fields transform as we have already seen. And the waves of these Z fields break spontaneously both U1 local symmetry and also CP. So here is the challenge actually to construct U1 and CP invariant superpotential, which realizes the desired vacuum alignment to reproduce delta CKM in particular. At the same time, if symmetry non-linearly realized, which is not so, actually is maybe less usual in the normal flavor model building, then I have many questions here. So what's the example of such a symmetry? What is this new field tau? How these transformations and these composite scalars look like? So I will address it in the second part of my talk, but the upshot that actually I will consider modular invariance, which will be an example of such a symmetry. And the advantage here that actually I need only one complex scalar field tau, which breaks both flavor symmetry and CP symmetry and can lead to observable CP violation. But let's go step by step. So what is this modular invariance? So modular invariance actually is unusual in quantum field theory, but very often encountered in string theory compactifications, because superstring theory requires 10 dimensions, so 6 of these dimensions have to be compactified. And one of the simple compactifications is on a product of 3 two-dimensional torus. So each two-dimensional torus is mathematically isomorphic to a lattice on a plane. And the lattice is characterized by 2 basis vectors, omega-1 and omega-2. And I will call the ratio of these basis vectors as a modulus. So now imagine that I perform some basis transformation of this lattice. Of course, lattice remains invariant under the basis transformation. But if lattice stays invariant, also a torus does so. And if I write this basis transformation realized on this modulus, it is nothing but linear fractional transformations with these coefficients a, b, c, d being integer numbers and the determinant of this matrix being 1. So actually it turns out that these transformations form an infinite discrete group. And you see that actually acting on tau, indeed, it is a nonlinear transformation. So this infinite discrete group actually turns out to be isomorphic to a SL2Z, so a group of 2 by 2 matrices with integer elements and the determinant 1. And actually it's huge infinite but discrete group can be generated by only 2 elements, S and T. So when acting on tau, this S realizes so-called duality transformation, taking tau to its inverse up to a sign, and T is a discrete shift symmetry, it shifts tau by 1 unit. And actually this tau, so a priori it lives in the upper half complex plane, but by the virtue of modular transformations, actually all inequivalent values of tau can be brought in this shaded strip, which is called fundamental region. So any 2 values of tau inside of this strip are not related by a modular transformation. Okay, so then I will think about this tau, I will promote it to a field. So if I think about it as a field, actually for each value of tau inside this region, a symmetry will be completely broken, except for 3 specific points in this moduli space, which is tau equals I, tau equals qubit root of unity, and tau equals infinity, which preserves certain residual discrete symmetries. Okay, so then what is nice about this modular group? That there exist functions, specific functions associated to it, which are called modular forms. So modular forms, they are holomorphic functions on the upper half complex plane, which transform under the modular group in a very well-defined way. So basically, if I apply this modular transformation to tau, this modular form goes to itself up to this prefactor here, which is characterized by a number k, which is known as a weight, which should be a non-negative even integer. And these functions, they have been studied by mathematicians a lot, and so we are fortunate because we know what they are. And in particular, all of them can be expressed in terms of so-called Eisenstein series. So Eisenstein series is some special function of tau given here, but what is important for us that for any weight k, actually a modular form can be written as a polynomial in only two basis functions, e4 and e6. So as written here. So to be more specific, let's say if I take weight 0, the only holomorphic function, which is modular form, is a constant, and actually a real constant in theories with CP. So weight 2 is special, there is no holomorphic function, and weight 4 and 6 we have one basis function, and up to weight 12 actually we have only one. At weight 12 we have two different independent functions, e4 cube and e6 square, and this will be important. So now let me go back to my supersymmetry action, which now depend on these matter fields and tau. And I want also to ask invariance under modular transformation. Actually, this has been studied already a long time ago by Ferrara and collaborators, and 7 years ago revived by Ferruccio Ferruglio, who also proposed some original points, which I will discuss later. So we have already seen how tau transforms. So now tau is promoted to a dimensionless superfield. So the matter fields, they transform very similar to modular forms, but now these weights are not restricted to be non-negative integers. So now I also see here how this lambda transformation I showed before looks like. Finally, vector supermultiplets, they also undergo certain transformations. And a crucial point here that actually, as you can see, also on field space, the symmetry acts non-linearly, so is non-linearly realized, unlike traditional flavor symmetries. So then, in order for the action to be invariant under these transformations, the scalar potential is allowed to transform up to a so-called scalar transformation, so a holomorphic function of the fields, which will vanish upon integration over the whole superspace. And superpotential should stay invariant, and gauge kinetic function, which incorporates in particular this theta QCD term, also should remain invariant. So now let me give you a concrete example. So it's easy to write a minimal form of scalar potential, not the most general one, but the one which satisfies the requirement. So there is some piece which involves only the modulus, and then the piece with matter fields, but you see that actually for each value of tau, these kinetic terms for matter fields are not canonically normalized. So I will come back to this point later. Then a crucial part is the superpotential. So now I know how my fields transform, and I can conclude that ukavas, which are tau-dependent quantities now, should transform in this very specific way. So they are nothing but modular forms of a certain weight, and this means that actually each element of the Yukawa matrix is a modular form, up to some real constant, real because of CP. Finally, gauge kinetic function is also real because the bare theta QCD is not there, since we assumed that full UV theory is CP invariant. Okay, so 2 words about modular invariance and CP. This we studied already 5 years ago with Sergei Petkov, Joao Penedo, and Pavel Novichkov. And here I just summarize. So what happens under CP? Matter fields, as usual, they get conjugated. Tau also gets conjugated up to a sign because of our convention. And then these modular forms, these composite scalars, actually under CP, they also get conjugated. So then the question is, where in this fundamental region, CP is violated, because now the only source of CP violation is the wave of this new field tau. And actually, it can be shown that CP violated everywhere except for these green lines here, which actually lie on the boundary of this fundamental region and on the imaginary axis. Okay, so now let us go back to our quark mass matrices, which are proportional to Yukawas. So the Higgs waves, they are real because we assume the CP invariant theory. And then I said that each element of the Yukawa is a modular form of a certain weight Kij. Okay, but modular forms, they are nice, because if I take a product of two modular forms, I also get a modular form. And basically, I'm interested in computing the determinant, and the determinant is the product of the elements. So then we end up with a conclusion that the determinant is a modular form of a weight given by the sum, for example, of the weights of these elements on the diagonal. And here you already recognize something what we wished for, no? The sum over right-handed and left-handed quarks over the generations, and also Higgses. So then the object of interest, the determinant of the full quark mass matrix, given by this product here, is a modular form of weight k det, written here. And if this k det is 0, then I'm done, because I know that the only modular form of zero weight is a real constant. However, so then one can say that, okay, I did something and I got what I wished for. And this is true. However, I want to say that this condition, k det 0, actually arises from the quantum consistency of the theory. And this goes as follows. So, as I mentioned, actually the kinetic terms, they are not canonically normalized. So for each wave of tau, I need to normalize my matter fields canonically. And then if I look at how modular symmetry acts on the canonically normalized fermion fields, this psi here, I end up with the fact that actually modular transformation is nothing but phase rotation, which depends on tau. And tau in turn depends on X, because the new field. However, the let's say the phase rotations on the chiral fields, the local phase rotations, they are usually dangerous because they lead to anomalies. And anomalies, gauge anomalies, should be cancelled. And indeed, is not an exception here. So we have a bunch of mixed modular standard model gauge anomalies, and all of them have to be cancelled for the theory to be consistent. In particular, we have mixed modular QCD anomaly, denoted here by A. So here I write the conditions for cancellation of these mixed standard model modular anomalies. So mixed modular SU2 left anomaly, and also modular U1 hypercharge anomaly. So we have a set of conditions, and simplest solution to these conditions actually is to cancel the anomalies across the fermion generations. So namely, I assign the weight minus k, 0k to 3 fermion generations, and furthermore assume that the sum of the weights of the Higgses is 0. But then if I take now these two conditions, so A, mixed modular QCD anomaly, with the sum of the Higgs weights 0 together, this implies nothing but the fact that the determinant of quark mass matrix is a modular form of weight 0. So this is somehow very nice. Now let me go to a concrete example, simplest example for quarks. So I assume 3 generation of quarks, assign weights minus 6, 0, 6, and assume that Higgs, they are not charged under modular symmetry. Then I immediately can write my Yukawa matrices. So for example, here I put 0 because there is no modular forms of negative weights, no? So all these zeros, they are protected by modular symmetry. Then I have these real constants on the anti-diagonal, and complexity sits in this lower triangular block. So after canonical normalization of the fields, I pick some factors of 2m tau in appropriate power. So these factors, they help actually to make the structure of the Yukawas hierarchical. So of course the determinant is real, it does not depend on tau. And then I fix my tau to some value in this modular space, fix also tangent beta to a certain value, perform a numerical search, and find that actually all quark masses, mixing angles, and most importantly, delta CKM can be reproduced with the coefficients of the same order. So as a nice byproduct, now I also can explain the flavour observables. Of course, here I cannot say I have a solution of the flavour problem because I have many coefficients, but the nice fact that all these coefficients have the same order of magnitude. Okay, this setup can be also extended to leptons. Here in particular, I assume a Weinberg operator to generate neutrino masses. Again, the textures, they are the same as in the quark sector. However, since neutrino mixing angles are large, we see that now we encounter certain hierarchy in these coefficients in the neutrino sector. But we, again, are able to reproduce the lepton masses and mixing angles, including also delta PMNs. Okay, so then one can build less minimal models with higher modular weights, but the morale is always the same. So I have these zeros protected by the symmetry and the real determinant. Okay, then let's go and spend some time about finite modular groups, because actually this is what Ferrulli proposed, applying to flavour. So the point is, and actually this is how we phenomenologists got interested in this, because the point is that this huge infinite discrete SL2Z group has a number of normal subgroups, these so-called principal congruent subgroups written here. And a nice fact that if I take the quotient of the full modular group with respect to this normal subgroup, the resultant group is finite. And actually for small n, which is called level, this finite group is isomorphic to groups like S3, A4, etc., which were used a lot in neutrino flavour model building. And then on top of this prefactor characterized by the modular weight, we can also ask the invariance under the finite modular group. So this introduces this row, the representation of the finite modular group. So now if I look at my superpotential, which schematically written here, so in addition to this balance of modular weights, I also should require that the product of the representations of the Yukawa and matter fields contain an invariant singlet. And actually, okay, why it is interesting? Because it in leptons, actually, it helps to reduce the number of free parameters, because you saw in my description, the number of free parameters was large. However, recently there was a work by Sergei Petkov and Joao Pinedo, where they also working with only standard model quarks, investigated different non-trivial representations of this finite modular group, and the result was that actually it is impossible to simultaneously realize the proposed mechanism to solve the strong CP problem and successfully describe quark masses and mixins with higher dimensional representation. So the result that actually if you want both to work, representations should be one-dimensional. So then we are back to the fact that still in the Yukawa I have many free parameters. Actually, they found an example which has one parameter less than in what I showed, but they performed a very extensive scan, and somehow what is observed that the modular weights, they are large, and string friends, they say that string compactifications, they somehow favor smaller weights, maybe 2, 3, 4, but not 10, 12. And then the question is, how is it possible to get smaller weights and maybe also to make the higher dimensional representation to work? And the answer actually is yes, but one needs to invoke new matter fields, new heavy vector-like quarks. So for our proposal to work, they are not needed. But if they are present, then the mechanism also works. So assume I have, let's say, 3 large quarks, and I assign these charges -6, -2, 0 to them, and then I have a vector-like quark, so I assign charges p+2 and +6 to this heavy vector-like quark. So a full theory is anomaly-free. Then I have the usual story that the gauge kinetic function is real, determinant of full quark mass matrix is real, theta bar is 0. So how to see it in the EFT? So in the EFT, we will have the mass of the large quarks, which is given by this seesaw-like relation. And here, actually, you can appreciate how singularities may appear. Assume that I integrate out these heavy quarks, but they become massless at certain point of the moduli space. Then indeed, if the determinant of this heavy mass matrix becomes 0, then I have breakdown of EFT, and this is how singularities may appear in my low energy EFT. So now independently, the determinant of mass matrix of light and heavy quarks, they are not modular forms of 0 weight, but their product is. And so when I go to the EFT, actually I have some non-trivial dependence on tau of this argdet of M light. But what happens that the gauge kinetic function in the EFT acquires a new contribution, which arises from the integration over these heavy quarks. And this contribution is such that it cancels exactly the contribution of the light quarks. So despite in the EFT I have anomalous field content, the full result is, of course, matches the result of the full theory, and namely that theta bar is 0. And in this recent work, actually, we considered the extension of Nelson bar model. So we introduce a bunch of vector-like quarks, which are singlets of SU2 left. So let's focus on the D sector. So let's say P of these new heavy fields. So now, of course, my superpotential contains more terms, and the full quark mass matrix has this form. So this light mass matrix, heavy mass matrix, and the mixed. So the blue entries here, they actually fill the electroweak symmetry breaking, so they are proportional to the Higgs wave, and the red terms, they actually don't fill electroweak symmetry. So then I have this seesaw-like relation, but the full quark mass matrix also should be obtained canonizing the kinetic terms. So this is how this KQC and KQ arise. And in particular, so this is the extension of the Nelson bar models, because in the Nelson bar limit, this small n is 0, and this capital N actually depends on these Z fields. In particular, it can be seen from here that in the pure typical Nelson bar setup, this delta sigma m originates purely from this wave function renormalization factors KQ and KQC. So we built some model based on modular invariance, but in addition also requiring invariance under this gamma 2 group, which is isomorphic to S3. So assigning quarks in particular to 2+1 representation of this group. So, and you see that actually indeed here I can have smaller modular weights, no, by absolute value smaller than 2. And then, okay, so here I will not go very much into the details, but I will tell you that we performed again the numerical scan, so we can fit all quark observables. And the nice thing here that now we achieved our aim that we have smaller modular weights, and also we have a high-dimensional representation of these finite modular groups. However, the negative part that still this does not help to reduce the number of parameters, because in total we have 15 dimensionless parameters to describe 8 dimensionless observables in the quark sector, which are written here. All right, so before conclusion, let me go and discuss the corrections, because of course I presented you with the result, but this result holds, let's say, at 3 level, and assuming that supersymmetry is exact. And indeed, as long as supersymmetry is exact, everything is good, because modular invariance is very powerful in the sense that it determines completely the functional dependence of the superpotential on this new field tau. So this is not the case for the Kähler potential, but actually very nicely, this theta bar parameter is a holomorphic observable, and such it does not depend on K, on Kähler potential, unlike the mass mixing parameters. Furthermore, there are also non-renormalization theorems in supersymmetry, which say that if some quantity is zero at some scale, then as long as supersymmetry is exact, it does not run. So, but we know that supersymmetry is not at low energy, so it should be broken, and supersymmetry breaking corrections, in principle, they can be large in the most general setup. However, there are certain regimes, in particular, if the scale of this flavour and CP symmetry breaking is separated from the scale of supersymmetry breaking mediation, then, and if soft supersymmetry breaking terms respect the flavour structure of the standard model, then these corrections can be estimated, and actually they turn out to be negligible. Finally, there are also corrections from the standard model dynamics, from the standard model loops, but those were estimated a long time ago, and actually the conclusion that the leading contribution arises at 4 loops in the standard model, and it is of order of 10 to the minus 18. So this is to say that, okay, so what I presented to you with relies on supersymmetry, but under certain conditions on supersymmetry breaking, the result is safe. So conclusions. I presented you with general conditions to solve the strong CP problem in theories based on spontaneous CP violation. So as we have seen, these conditions, they actually can be implemented with the help of anomaly-free local flavor symmetry, which can be either U1 or modular or maybe something else. So one can think. Then I presented you with this modular invariance, which is inherent to toroidal compactifications in string theory. However, it can be consistently implemented in a bottom-up fashion in a supersymmetric QFT. And the nice point here that the wave of this modulus tau is the only source of spontaneous CP and flavor symmetry breaking. So the strong CP problem gets resolved in 2 steps. So a bare theta QCD term is 0 because the full theory is CP conserving. And this arc depth of full quark mass matrix is 0 because of anomaly-free modular invariance. So heavy vector-like quarks are not needed, unlike in the Nelson bar scenarios, but they can help to lower modular weight if one wants to, for example, realize this construction, or try to realize this construction from a concrete superstring compactification. Finally, corrections should be taken with care, but can be made negligible if certain assumptions on supersymmetry breaking are held. Okay, thank you very much for your attention.
Thank you very much for the very nice talk. So let's remind everybody that you can ask questions via the YouTube live chat system. Now, this usually take there's a bit of a delay. There are a couple of seconds of delay, so maybe we can start with questions from the people in the Zoom session while we wait for the questions from YouTube. I don't know if Roberto, Nicolas have any questions. I have a couple. Okay, so maybe I'll start. Okay, so first of all, okay, you have done this in the context of a supersymmetry. So in principle, these modular forms or U1 symmetries, they will give you the shape of the Yukawas, but they should also give you the shape of the soft SUSY breaking terms. So this in principle can contribute to things like lepton flavor violation, like mu gamma, and mixing on the meson sector can give you contributions to epsilon k, or even give you contributions to the EDM. So I was wondering if you have calculated this in the context of the SUSY contribution.
Yeah, good question. No, so basically this we did not do because we just assume that these soft supersymmetry breaking terms should have the same flavor structure as the standard model fermions. But in principle, one could try to build the full model, also specifying this soft supersymmetry breaking term and see what the implications are. However, here now, as you can see, the hierarchy of scales I have in mind is the following: that the flavor and CP are actually broken at much higher scale than the SUSY. So then probably at this scale, one needs to think, so what survives, no? Because somehow the hierarchy of scale, that first I break flavor, and then I break SUSY. So I should be, in particular for these corrections to be small, there should be this separation of scales. But yeah, it would be probably interesting to give a concrete example. We did not do that.
Mm-hmm. Mm-hmm. So basically, you're. I mean, apart from the separation of scales, you're assuming like a minimal flavor violation structure for the soft
Kind
SUSY.
of, yes, kind of.
And so I guess that in the context of an effective field theory, you can also make these higher dimensional operators that contribute to all these observables. You would assume the same thing, right? That they would have a structure following the Yukawas.
Yeah, this is somehow important not to spoil the desired result with potentially large corrections.
But in a way, this could also help you constrain the parameters, right? Because if maybe you don't assume this minimal flavor relation structure, you could constrain some parameters, because you at the end said that you had like 15 parameters and 8.
Yeah, in this. So for example, in a simple model, still, yeah, we have many, because let's say we have 7 real constants per sector. So will be 14 constants plus tau. So here is a bit like Frogat-Nielsen, no? So I can describe, but actually I cannot predict. And this is why there was somehow hope introducing this non-abelian groups helps to reduce. But unfortunately, here probably is a bit of a usual story that quarks don't seem to like much this non-abelian structure. So they still require more parameters.
I see. Yeah. Okay. Cool. Okay. Well, I have a couple more questions, but maybe Roberto, Nicolas, or maybe there's something. No questions in YouTube at the moment. Roberto, go ahead.
Yes, I have a question for, first of all, very interesting the model. I mean, how to achieve not to have the action. So in that line with since you don't have action in this scenario, in this realization, can the model hypothetically have some kind of particle that replace the action in the sense of a kind of dark matter candidate or something like that? Or
yeah, this is a
in that sense, related with that, with the same question, R parity, like to have the neutralino in case, is still feasible in the model, or it got a little bit messed up this part?
Yeah, no, this is a good question because so it may happen that actually everything is solved at a very high scale, but there is no observable consequence. However, so this tau, which I promote to a superfield, in principle, it has a scalar component and also fermion component. And till now, actually, what we need is only the wave of the scalar component. And we assume actually that the rest is very heavy, and if it is somehow produced and it decays, so it does not have any consequence. But in principle, no, the one could think that if this, for example, fermionic component of tau, like moduli, can be such that, for example, to account for dark matter, but then one needs to look at the dynamics of the interactions between this, let's say, super partner, tau, and the rest, and assume that actually the couplings between them are not Planck suppressed and can have some viable, or some significant consequences. Yeah, phenomenology here actually is very minimal, no? So in a sense that apart from the flavor observables so far, it's hard to, so here I cannot tell you, look, I have some prediction of a large scalar degree of freedom, and we should, so it can be that actually everything is solved, but no experimental consequence. Yeah, so probably here I had some thoughts about this, but is what I said, maybe this moduli, can somehow have some implication, but we did not look at it.
Thank you.
Let me ask one more question, because you presented neutrino masses. Since we're talking about dark matter, let's talk about the other problem, which is neutrino masses. So in principle, what you did is you introduced neutrino masses via the Weinberg operator, right? So the Weinberg operator in principle should come from like a CISO mechanism or something like this. I don't know if you have done that extension with, because CISO in the
after the original work by Ferrulio 7 years ago, then there was a big activity in which I also participated, basically looking only at the lepton sector and building models. In particular, we did a very systematic investigation of CISO type 1 models with this modular symmetry. And the crucial thing that in the leptons, this trick or this proposal to introduce this non-abelian finite modular group actually works, because it allows one to reduce drastically the number of parameters. For example, we have, to my knowledge, the minimal model, let's say, has 4 parameters, including tau, so 2 degrees of freedom from tau plus 2 Lagrangian couplings, in order to describe and predict 9 observables in the neutrino sector. So 3 masses, 3 angles, and 3 CP violation phases, assuming neutrinos are Majorana. So there, this really helps. And yeah, this we did extensively. So then people also did separately quarks. There, the situation that, to my knowledge, the best model maybe requires 9 parameter or 8 parameters to describe 10 quark observables. So already the score in terms of number of parameters is not so good. Then people also tried the unified models. So here we did not actually try to minimize the number of the parameters. So for us here it comes more like byproduct of our new mechanisms to solve the strong CP problem. But in principle, it would be a dream to have a unified model with relatively few parameters where these mechanisms can be implemented and all flavor observables can be either described or better predicted. But this is in progress.
Yeah. Super. So we do not have any questions from YouTube. We're running out of time. Maybe some urgent question from Roberto or Nicolas? No urgent questions. Okay, great. So thank you very much, Arsenii, for the very, very nice talk. It's been
thanks a lot for the invitation. I hope it is a bit mathematical, but I hope I tried to keep some compromise.
But then one can review the video later, putting pause, right, and doing the calculations.
Yes.
Perfect.
Yes. Anyway, thanks a lot for the invitation.
Before we log off, let me remind all viewers that in 2 weeks, we have a colloquium. We haven't had a colloquium in 2 years. The last one was in 2022. So now we are having a colloquium on sustainability in particle physics, right? So please stay tuned, and we'll see you in 2 weeks. We'll have Pete Millington giving this talk. Okay, great. So we'll see you all next time. Thank you very much, once again.
Thanks a lot.